Kia ora, year 11 and 12. This video is a really nice question from the winter 2017 A-level paper, and it's got both integration and iterative methods in it. So this is the question here. In this video, I'm just going to do the integration part, but I want to show you the whole lot so that you get a feel for kind of how the flow of the problem is going to go. So the first bit is the hardest bit, and it's an integration setup. So we're given this integral. Where's my highlighter pen? So we're given this integral is equal to 2, and a is some positive constant, and it's greater than 1. And we have to work with that to show that a to the power of 3 over 2 is equal to all of this. Now, when you see that, you should notice that in the setup of that equation, we've got a to the power of 3 over 2 here, and we've got a to the power of 3 over 2 here, and we've still got log of a down here. So you should get a feel that this is going to be a question where we use a fixed point iteration and end up seeing if we can get a convergent sequence to figure out a value of a. And sure enough, that's what the second part of the question is going to do. But the first part is doing the integration, right? So what we're going to do is we're going to integrate this thing here with these limits, and that's going to give me a value of the integral that has got a's in it. And then we're going to equate that to 2, and we're going to muck around with all of that to show this. Now, let's take a look at just the integration on a different page. So here's the integral a little bit bigger. We've so far done quite a lot of substitution and quite a lot of backwards chain rule, with me just telling you that you need to get more fluent at backwards chain rule. But this integral is neither of those things. It's a product, but it's a product where we haven't got the derivative of this thing sitting here. These two things are kind of unrelated. So remember, the happy kind of product integrals are where I've got sine x cos to the power of, I don't know, 19x dx. So let's just go over why this one is a really nice, easy one. And it comes back to the chain rule, right? Because I see this and I go, well, what happens if I raise that to the 20th power? And then I think about differentiating that. Well, when I differentiate it, the first thing that's going to happen is I'm going to have 20 come down. So we need to undo the impact of that by timesing by 1 over 20. But when I'm using the chain rule, I have to think about cosine of x as the inside function. And the derivative of cosine of x is negative sine x. So when I differentiate this, I'll end up getting a sine x popping up. Now, it needs to be negative to undo that impact. But basically, this integral is pretty easy once you've seen that pattern a few times. So let's now go back to, that was a little digression, but I guess you're used to that by now. So up here, we've got no such luck. We've got x to the power of a half, and then we've got the natural log of x. Now, this thing here is a pain in the neck to integrate. We can do it actually using the method we're about to do on this one, which is called integration by parts. But not only have I got the log of x to integrate, I've got it times by x to the power of 1/2. So this is how integration by parts works. Now, this video, I'm making this before I teach this to you in class, if you're watching this in 2019. So you can follow through with what I'm doing, but we're going to do a proof of how it works in class and go a bit more slowly. But the basic idea with IBP is this. So we've got our integral, and we've got 2 bits in it. So what we're looking for is one of those functions to be a pain to integrate. And that's the one I've just underlined. So this one here, we're not going to think about integrating. We're going to do one of 2 things. We're going to leave it alone, and we're also going to differentiate it. This one here, we're going to integrate it. So when you look at a problem and you identify that it's an integration by parts problem, you're always thinking, well, which of those things am I going to choose to integrate? And sometimes you have a choice. And if you choose one way, it unravels really easily. And if you choose the other way, it's just a big disaster. So in this case, it's pretty obvious which one we should do. So IBP goes like this. And it is going to feel really weird to start with. We've got x to the power of a half times the natural log of x dx. So it's got 2 bits to it. The first bit is where we integrate this, giving me 2/3 x to the 3 over 2. And we leave this alone. And we evaluate that at the limits of the integral. And now we subtract this integral. So the integral from a to 1, and again we integrate this, and we times this, we differentiate this. Okay, so one more time, there's two functions in here. This one here ends up getting integrated in both bits of the integration by parts. It gets integrated in here, and then it gets integrated in here again. This one here gets left alone for the first part, and then it gets differentiated the second time, right? So here it is getting left alone, and here it is getting differentiated. So I'm just going to erase that. Let's get rid of this. So now we have to keep on going. IBP does take a wee bit of work. So I'm just going to let this integral sit here. I could go in and start working it out. It's usually, I think, better to leave that till the end, because sometimes you'll get some common factors from the two. Now, what have I got now? Well, I've got the integral from a to 1 of 2/3 x to the power of 1/2. So suddenly this has got really, really doable. So I've got this integral minus, what have we got here? Well, 2/3 times 2/3 x to the 3/2 between a and 1. Now I'm going to write that as one big integral. And so we've done all the hard bit now. We've just got to be careful. So we're going to take out that 2/3 common factor. So we've got 2/3 of x to the 3/2 log x minus 2/3 x to the 3/2 from a to 1. I can do things with that. I can factorize, but basically all I've got to do now is substitute these two things in. So this is equal to 2/3 of a to the 3/2 log a minus 2/3 a to the 3/2 minus 1 times log of 1, which is 0, minus 2/3 times 1 to the 3/2. So let's clean that up. We've got this is equal to 2/3 of a to the 3/2 log a minus this plus 2/3. And I know that this whole thing is equal to 2, right? Because we were told that at the start. So this is what I'm now going to work with, and it's a show that question. So let's just quickly go back and see what we've got to show that. Right, we've got to show that a to the 3/2 is equal to that thing there. So I just want to check my notes that I haven't mucked any of this up, but I think we're pretty good. So I'm going to do some rearranging, and we get, so let's write it up nicely. 2 is equal to 2/3. I've got a to the 3/2 log of a minus, what have I got now? 2/3 plus 4/9, right? So I'm just expanding out this bracket here, 2/3 times 2/3. So I'm going to subtract this first of all, giving me 14/9 is equal to 2/3 times this. Rearranging that, what do we get? Well, I'm going to try and make a to the power of 3/2 the subject, because this is where I'm trying to head here. So let's work our way through that. So I get 42/18, which is a pretty ugly fraction, is equal to a to the 3/2 log a minus a to the 3/2 times 2/3. Cleaning up this, we've got a common factor in here of 6, so this is 7/3. It's worth just noting where we're trying to go, I think, on this screen. We're trying to get to this. A to the 3/2 is equal to 7 plus 2a to the 3/2 divided by 3 log a. So multiplying through by 3 gets me just about there. 7 is equal to 3a to the 3/2 log a minus 2a to the 3/2. So let's work with making this one the subject now. We're going to have 7 plus 2a to the 3/2 is equal to 3a to the 3/2 log a, and I'm going to divide through by this. So 7 plus 2a to the 3/2 over 3 log a is equal to a to the power of 3/2. As required. Okay, we could put in a nice little arrow in there from the line above. Okay, so that's the first part done, and you can see that that was pretty slow, but that took 11.5 minutes. So I'm going to now just go back and talk a bit about how you do the next bit. We need to show by calculation that A lies between 2 and 4. Now we're doing that because we've got A just about everywhere in that expression. We've got A on the left-hand side, we've got A here and A here. So what I'm looking for is a change of sign. So I'm going to set up f of x as equal to the left-hand side, at the moment, a to the 3/2 minus this. Right, and I'm going to show that when I substitute in 2, I get something with a positive or a negative, and I get the opposite sign for that. So we're looking for a change of sign. If you can't remember that, you need to go back through chapter 6 in the book. And then this next part is really easy for 3 marks, as long as you don't muck your calculator up. You're going to give each iteration to 5 dp, and then you're going to work out A. So I will do a video on that, but I'm not going to do that tonight because this is long enough already. Thanks for watching. One last thing, if anyone is still watching, if this is your first integration by parts example, you are going to have found this really, really hard, right? This is not a straightforward IBP example because we're working with these limits being A and 1. So if you go to exercise 80 in the textbook and get really confident with those questions first, and then come back and redo this exam question, you should find it quite straightforward. Thanks for watching.